In this video, we are going to be learning about light and electromagnetic radiation. This topic is important because our understanding of how light interacts with matter has played a major role in shaping what we know about atomic structure. Earlier in this course, we learned that atoms contain a nucleus surrounded by electrons. However, it was observations involving light interacting with matter that showed the simple picture was incomplete. After the nuclear model was proposed, Niels Bohr introduced a model where electrons orbit the nucleus in fixed paths, similar to planets orbiting the Sun. Later, Erwin Schrödinger and other scientists developed the quantum mechanical model, which more accurately describes how electrons behave around the nucleus. While the quantum mechanical model involves advanced mathematics, in this course we will focus on conceptual understanding rather than mathematical details. To understand how atomic models developed, we first need to understand what light actually is. Light is a form of electromagnetic radiation. Electromagnetic radiation consists of oscillating electric and magnetic fields that travel through space together, as shown in this image. Light also exhibits wave-particle duality, meaning it behaves like a wave in some situations and like a particle in others. When light behaves as a particle, we refer to it as a photon. Waves can be described using several characteristics. One important feature is amplitude, which is the height of the wave measured from the center line to the top of the crest. The amplitude of a wave is related to the brightness. A larger amplitude means brighter light. Another important property is wavelength, which is the distance between two consecutive peaks of a wave. Wavelength is represented by the Greek letter lambda. Because wavelength is a distance, it is measured in units such as meters or nanometers. As waves travel through space, we can also consider how often the wave peaks pass through a given point. In this animation, the red wave has a longer wavelength, so it passes through the edge of the image less frequently than the peaks of the purple wave. This idea leads us to frequency, which describes how often a wave peak passes through a specific point in a given amount of time. Frequency is represented by the Greek letter nu and is measured in hertz, which means cycles per second, or 1 divided by seconds. Wavelength and frequency are inversely related. Waves with longer wavelengths have lower frequencies, and waves with shorter frequencies have higher frequencies. Although light can have many different combinations of wavelength and frequency, all electromagnetic radiation travels at the same speed in a vacuum. Multiplying the wavelength times the frequency gives us the speed of light. The speed of light, represented by the symbol c, has a value of 2.998 times 10 to the 8th meters per second. To put that in perspective, that is equivalent to 186,000 miles per second, fast enough to orbit the Earth 7 times in 1 second. While the speed of light is constant, the energy of light depends on its frequency. Shorter wavelengths correspond to higher frequencies and therefore higher energies. Energy is directly proportional to frequency. As frequency increases, energy increases. The electromagnetic spectrum shows all possible types of electromagnetic radiation, arranged by wavelength and frequency. Low energy radiation has long wavelengths, while high energy radiation has short wavelengths. The spectrum includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. The visible spectrum is the only part of the spectrum that humans can see. If we zoom in on the visible light, we see a range of colors arranged in a specific order. Red light appears next to infrared radiation and has the longest wavelength within the visible spectrum. Violet light appears next to the ultraviolet radiation and has the shortest wavelength. The colors of visible light always appear in the same order, which matches the colors of a rainbow. A helpful way to remember this order is the acronym Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. Let's work through an example problem. Dr. Yu is 1.60 meters tall. A wave with a wavelength of 1.60 meters falls into which region of the electromagnetic spectrum? After that, we will calculate the frequency of this radiation. First, we identified the wavelength as 1.60 meters, which can be written as 1.60 times 10 to the 0 meters per second. Looking at the wavelength scale on the electromagnetic spectrum, this value falls into the radio waves region. Now let's calculate the frequency. The relationship between speed, wavelength, and frequency is given by the equation C is equal to lambda times nu. We are solving for frequency, so we divide both sides of the equation by wavelength. The speed of light is equal to 2.998 times 10 to the 8th meters per second. Dividing this wavelength by 1.60 meters causes the meters to cancel out, leaving the units of per second. Performing the calculation gives us a frequency of 1.87 times 10 to the 8th meters per second, or you could say 1.87 times 10 to the 8th hertz. This value is reported to 3 significant figures to match the given wavelength. Now for a practice question. Based on the electromagnetic spectrum, which type of visible light has the lowest energy? Red, green, or blue? The correct answer is red light, because it has the longest wavelength and therefore has the lowest energy. Which type of radiation has the highest frequency? Radio waves, infrared radiation, or X-rays? The correct answer is X-rays, since higher frequency corresponds to higher energy and shorter wavelength. In the early days of atomic research, scientists used flame tests to help identify elements. When heated, each element produced a characteristic flame color, similar to how fireworks emit light in different colors, or neon lights emit different colors. However, as more elements were discovered, it became difficult to distinguish subtle differences in flame colors. To improve accuracy, scientists passed the emitted light through a prism, separating it into individual wavelengths. This revealed that each element produces a unique emission spectrum consisting of specific bright lines rather than a continuous rainbow. These emission spectrums act like fingerprints for the elements. Importantly, the presence of discrete lines and gaps where there is no light emitted showed that electrons could not exist at just any energy level. This observation could not be explained by the nuclear model of the atom, providing key evidence that electrons occupy specific energy states. These findings ultimately helped and led to the development of the quantum mechanical model of the atom.